Hello students. So from the today's lecture, we are going to start infrared spectroscopy. So for the infrared region, the frequency is 3 into 10 raised to 12 to 3 into 10 raised to 14 Hertz. Talking in terms of wavelength, it is 100 micrometer to 1 micrometer. So in the previous chapter, we have seen that the rotational spectroscopy, in which while the molecule rotate about a specific axis, it absorbs some energy, it gets excited, it emits some energy, and whatever energy it emits, according to that we have done the spectroscopic determination. So in the today's lecture or in the infrared spectroscopy, there is a study of vibration of the molecule. So it is also called as a vibrational spectroscopy. Is it clear? It is also known as a vibrational spectroscopy. So in the previous chapter we have studied that as the energy level was increased, the radius or the internuclear distance also increases. So in that we have assumed that there must be the elasticity in the bond. That means what? The bond must get compressed or stretched. That is, it is in continuous motion. So that the elasticity of bond we have studied in the previous chapter. So now we will start with the vibrating diatomic molecule. In that we are going to study the energy of a diatomic molecule. Okay. So first of all we have to assume a molecule, a diatomic molecule. See, this is a diatomic molecule. So what happens in the diatomic molecule? That there is a repulsion between positively charged nucleus and also between negatively charged electron cloud. Okay, so if this is a nucleus, this nucleus repels with this another nucleus. Similarly, this electron repels the electrons of the another atom. So there is a repulsive force. But there is also an attractive force, an attraction between an oppositely charged nucleus of one atom with positively charged here we can say negatively charged electrons. Is it okay? So talking about the diatomic molecule, there is a repulsive force as well as the attractive force. Is it okay? Then what happens? Then the atom sits at a mean distance at which the attractive force and repulsive force gets stable. Okay, so that the energy of molecule gets minimized. It gets minimized. Is it okay? So what happens, as there is an attractive force and repulsive force at a distance where both the forces get stable, at that point the molecule gets stable. And as we say that lesser is the energy of molecule, more is it is a stable. So at that distance what happens, the energy of that molecule becomes stable. So now if we pull or push the atoms away from each other or towards each other, the energy of system increases. So why it increases? Because whatever the stable distance at which the both force get stable, that get disturbed, and due to that the molecule becomes unstable, and that is why the energy of the system gets increased. So now the compression or extension of a bond is like to behave as spring. That means it obeys Hooke's law. So as we are telling that the bond gets compressed and extend, so it behaves as a spring. So what happens, as it behaves as a spring, we know the law that is a Hooke's law for the restoring force, that is F is equal to minus K into bracket R minus R equilibrium. So what is this R? R is a bond length. R equilibrium is what? The equilibrium distance. Is it okay? That means F is restoring force. That means this force try to stable that molecule. K is the force constant and R is the internuclear distance. So E is equal to half K R minus R equilibrium square. Is it okay? So now this model of vibrating diatomic molecule, that is called as a simple harmonic oscillator. So we will see for what happens for the simple harmonic oscillator. So now speaking about the simple harmonic oscillator. So in the simple harmonic oscillator, R, that is an equilibrium, is equal to the equilibrium distance. Okay. So in that, what you have to do? We will draw one diagram. So see student, this is a diagram in which there is a internuclear distance versus energy plot for the HCl molecule. HCl is a diatomic molecule. So see, this is a equilibrium, R equilibrium. So at this distance, what happens? The HCl molecule is stable. So if we compress the distance between the H and Cl, what happens? As we decrease the distance between them, the energy gets increased. Similarly, when we pull the H atom outward or away from the chlorine, again the energy increases. That means at this the energy is 0. So at this distance or at this internuclear distance, this HCl molecule gets stabilized. So this implies that when we compress the molecule, energy increases. Also when we extend or pull the molecule outward, then also the energy increases. So here there is one consideration that this epsilon 1 and epsilon 2 arises due to the compression or extension. Is it okay? So in this, the Cl atom is considered at the stable at the R is equal to 0, while H atom oscillates from H dash position to H double dash. So its position varies. That means what? The heavy atom is kept at fixed position and lighter atom is oscillating. Is it okay? It is getting oscillated. When epsilon 1 energy is reached, the atom will oscillate more vigorously. That means it will oscillate more vigorously. Why it will oscillate more vigorously? Because as the energy increases, the molecule becomes unstable. As the molecule becomes unstable, there is a continuous vibration in that molecule. So there must be some vibrational frequency. That means by that frequency it must be vibrating. So that vibrational frequency depends on what? It depends on mass and force constant but it does not depends on amount of distortion. That means what? Whether it is distorted largely or smallly, it does not affect on the vibrational frequency. It will vibrate with that frequency itself. but that frequency depends on the mass and the force constant. So that frequency is denoted by omega oscillation, and which is equal to 1 upon 2 pi into bracket k upon mu. So as we are talking about the frequency, it has the unit hertz. So this is a force constant k on which it depends, and also it depends on the mass. So this is a reduced mass. Is it okay? So the vibrating frequency depends on the reduced mass and the force constant. So when we convert it into the wave number, that means omega oscillation bar. It is denoted by bar. So which is equal to omega oscillation upon c, where the c is velocity of light. So what will happen to this equation? 1 upon 2 pi c into under root k upon mu. So it is, as it is a wave number, it is expressed in centimeter inverse. So this is the formula for the wave number, and the upward is the vibrational frequency. Is it okay? So the next point is, from the Schrodinger equation, the vibrational energy is quantized. So that energy is given by E nu is equal to nu plus 1 by 2 into h omega oscillation. This is expressed in joule, and value of nu is from 0, 1, 2 onwards, where nu is the vibrational quantum number. So in the rotational spectroscopy, we have the rotational quantum number. In the vibrational spectroscopy, we have the vibrational quantum number. So the value of vibrational quantum number is from 0, 1, 2. So now epsilon nu, that is a wave number, is equal to E nu upon hc. So now we know that 1 upon hc into nu plus 1 by 2 h omega oscillation. So now this h gets cancelled. What remains is a nu plus 1 by 2 omega oscillation upon c. We know that omega oscillation upon c is omega bar. Is it okay? That is omega bar. This is the value for epsilon nu. Now we will calculate the value of E nu and epsilon nu for nu is equal to 0. So E nu is equal to, when we put 0 here, what remains? 1/2. So E nu is equal to 1/2 h omega oscillation, and epsilon nu is equal to 1/2 omega bar oscillation. Is it clear? That means this is known as 0-point energy. That is, energy at nu is equal to 0. So what does this implies? This implies that the diatomic molecule can never have 0 vibrational, zero vibrational energy. Why? Because we assume that the atom itself has some vibration. It is not a stable atom. It always has some little vibrations. Because the atom cannot be, because the atom cannot be completely at rest. Okay, this is the reason. So the quantity 1/2 H omega oscillation or 1/2 omega bar oscillation is known as zero point energy. So there is always a question on 0 point energy. Okay, so the prediction of 0 point energy is the basic difference between the wave mechanics and the classical mechanics. So the classical mechanics would have no objection to molecule having no vibrations, but wave mechanics says that atom must possess the vibrations. Okay, so that is the difference between the wave mechanics and the classical mechanics. So now according to quantum mechanics, the selection rule is delta nu is equal to plus minus 1. So star this. Here comes the selection rule. You have to remember all the selections rule for each and every spectroscopy. To this condition, there is the most important thing that as the vibration changes, will give the vibrational spectrum. As the vibrational energy changes, it gives rise to vibrational spectrum. So as there will be change in vibrational energy, it will give the vibrational spectra with the radiation. Only if the vibration involves a change in dipole moment. Is it okay? So as there is a change in vibration energy, it will give rise to the vibrational spectrum, but only when there is a change in a dipole moment. Again, that condition of dipole moment arises here, that the molecule which will show the change in dipole moment will be vibrational active or IR active. So here I can write that heteronuclear atom or molecule would show the vibration spectra while homonuclear, it cannot be a molecule, it can be element, will be IR inactive. Is it okay? So now we can calculate the various vibrational energy levels. So see, it can be done by putting the values of nu for different nu values, and we can predict the value of energy. Okay. So now for nu is equal to 0, the energy will be half omega bar oscillation. Is it okay? So now for omega is equal to 1, it will be 3/2 omega bar oscillation. For nu is equal to 2, it will be 5/2 omega bar oscillation. For nu is equal to 3, it will be 7/2 omega bar oscillation. For nu is equal to 4, it will be 9/2 omega bar oscillation. Is it okay? So on this transition will do. And we know that the selection rule is delta nu is equal to plus minus 1. So only these transitions are allowed. Okay. So you can calculate many energy levels for this. So from the diagram, we come to know that the separation between two energy level is same. That means what? That means all are equally spaced. Is it okay? So now we will calculate the epsilon nu plus 1 by nu plus 1 to nu. So what happens? We know that nu plus 1 by 2 omega bar oscillation minus nu plus 1 by 2 omega bar of oscillation. So now nu plus 3/2 omega bar oscillation minus nu plus 1 by 2 omega bar oscillation. So now this nu omega bar oscillation plus 3/2 omega bar oscillation minus nu omega bar oscillation minus 1/2 omega bar oscillation. So this gets cancelled. What remains is 1 into omega bar of oscillation. Is it okay? This is the difference between the two energy levels. During the absorption, the vibrating molecule will absorb the energy only from the radiation with which it can coherently interact, and this must be the radiation of its own oscillation. So this is the sentence which I have talked. Okay, so here we will stop. Thank you.